The history of black holes isn't very long. 100 years ago, no one knew about black holes, but because of Einstein's theory of relativity, black holes were later discovered. There are two parts to the theory: the special theory of relativity and the general theory of relativity. The special theory of relativity, published by Einstein in 1905, tells us how speed influences time. If you're in a spaceship that is going very fast, if the speed is too high, time will slow down for you, relative to the people not on the spaceship. The word relative is very important because when you're in a spaceship, you won't feel the time slowing down. You would think that time is flowing at the same speed as it normally does. But when you get back to the Earth, you'll find out that there was a difference in the flow of time. This is known as kinematic time dilation. Not only speed, but even gravity can also result in time dilation, as shown by Einstein in his general theory of relativity. This was developed by him in 1915. The more gravitational force you would experience, the more time would slow down for you. This is known as gravitational time dilation, and this was depicted amazingly in Interstellar movie. When Cooper and his team land on the Aqua planet, 1 hour on that planet equals 7 years on Earth, because the planet is very close to the Gargantua black hole. So the gravitational force of the black hole impacted time. To visualize this, Einstein wanted us to imagine a space-time fabric on which all planetary objects are placed. The space-time fabric bends due to the mass of the objects. And when the mesh bends, not only does it attract physical objects more, but it also leads to time dilation and the other forms of energy, such as sound, heat, or light. Yes, that's right. This was another conclusion drawn by Einstein. Gravitation affects almost everything. Not only are physical objects attracted by the force of gravitation, but it also attracts heat, sound, and light. This means that there can be objects in the universe that have such a high gravitational force that they can completely absorb light. If there are such objects, it means that they would be completely black and we won't be able to see them because not even light can escape them. This is exactly what black holes are. But when Einstein presented his theory of general relativity, the concept of black holes was merely theoretical back then. Einstein knew that gravitation influenced light, and theoretically, objects that can absorb light are possible. But Einstein did not know that there were actual black holes. In fact, when Einstein was alive, the concept of black holes seemed weird to him. He knew that there can be such things theoretically, but then theoretically, the existence of infinity is also possible. But realistically and practically, he did not believe that such things existed in reality. By the time he passed away, the term black holes had been invented. An interesting fun fact here is that a key point in Einstein's theory was that light's speed limits is influenced by gravity. To use a practical example, suppose that the sun disappeared suddenly. As you know, we'll get to know this 8 minutes later about the disappearance of sun because it takes 8 minutes for sunlight to reach Earth. But according to Einstein, the gravitational impact of the sun's disappearance will also be felt 8 minutes later. Isn't it very interesting? After Einstein, the theory of general relativity was worked on by many scientists. There were several unsolved equations. They solved those equations and tried to derive the solutions. And by getting to the solution of these equations, it was theoretically proven that things like black holes do indeed exist. By the 1960s, researchers and scientists had finally agreed that, not only theoretically, but perhaps one day, realistically, we would be able to see black holes because these do exist in space. The term black hole was used for the first time by a magazine in 1964. But only after 1967, the term black hole gained popularity when physicist John Wheeler popularized it. Even though the term black hole sounds quite sensational, it is a misleading name. It might sound like there's an actual hole there, but that's not the case actually. There's no hole in the space. Black holes are formed by stars, so there's some material at its center. But in the stars, even though our sun is a star, there's a continuous nuclear fusion reaction at their center. These reactions produce heat and light. The heat being produced sends a force outward, and at the center of the star, there's the force of gravity, which helps the star remain intact and alive. This is how the stars maintain equilibrium throughout their lives. The forces pushing outwards due to the reaction and the forces pulling inwards due to gravity. But these reactions take place when a fuel exists. Either hydrogen or helium. The fuel wouldn't always be there. It would get burned up at some point. And when the fuel ends, there won't be any forces pushing outward, and the gravitational force pulling inwards wouldn't be countered by an equal force. So that star will collapse on itself because of its own gravity. By the way, this will take a long time. Our sun's life expectancy is around 10 billion years. But what happens next depends on the mass of the star. Let's look at the chart of the life cycle of a star. If the mass of the star isn't high, like if it was a small or average-sized star, it turns into a red giant, after which it can become a planetary nebula or a white dwarf. But if it was a huge star, and when it runs out of fuel, it cools down and turns into a red supergiant. And then the supergiant bursts and turns into a supernova. After this, a tiny core remains. If the core is tiny, it is called a neutron star, but anything bigger than that, we call it a black hole. Basically, the mass of the star after it collapses due to its gravitational force becomes small and condensed, and it can turn into a black hole. For a star as big as our sun, if that turns into a black hole, the diameter of that black hole will be merely 50 kilometers. Can you imagine the volume getting this small? But the interesting thing here is that our sun will not grow up to be a black hole. This was proven by an Indian-American astrophysicist. He developed the Chandrasekhar limit value. He said that the maximum mass of a white dwarf can be 1.4 times the mass of our sun, above which it cannot be stable and would turn into either a neutron star or a black hole, and our sun is under this limit. Let's now understand the types of black holes. There are mainly 3 or 4 types of black holes. The first is the stellar black hole. That is the most common type of black hole. These black holes were created by stars. Scientists estimate that in our Milky Way galaxy, there are anywhere between 10 million and 1 billion such black holes. Then there are the primordial black holes. These black holes are as small as an atom, but their mass is like that of a mountain. But it is just an assumption that they are as small as an atom. The third type of black hole is the supermassive black hole. These black holes are enormous. They are so big that their mass is more than that of 1 million suns combined, and it fits into a ball whose diameter is as big as that of our solar system. Scientists believe that at the center of every major galaxy, there is a supermassive black hole. The supermassive black hole at the center of our Milky Way galaxy is called Sagittarius A, and the black hole in the film Interstellar, which was named Gargantua, was said to be a supermassive black hole. Additionally, scientists believe that there may be a fourth type of black hole too. The fourth type of black hole will be an intermediate black hole, which lies somewhere between the sizes of stellar and supermassive black holes. Stay tuned for part 2, where we'll delve even deeper into the mind-bending science and mysteries surrounding black holes. Don't forget to subscribe and hit the notification bell so you won't miss the next part.